per region. And I'll give you an example in this case where that might be useful. Another thing is the idea of basically ganging all properties. So for example, very often the global settings are reused in equal coordinate systems. So for example, here by default the maximum step is applied everywhere for the torso, but we may want to change that for a specific axis. So we have this toggling function now which allows us to basically change the resolution in a single axis or in multiple axes or even in all three. We can gang those again and now everything is set to the same. So this is a new concept, and the idea behind that is to sort of hide many parameters which are only used seldomly, so not to overload the interface, to make it a bit more intuitive. So all of these ideas are present in 14.8. And let's have a look now at this specific example. We're going to go back now to our antenna. Let's just zoom in a little bit here. Can close that for now. And I'm going to change the template here to the geometrical mode. And as before, we have these shortcut keys. So using the numerics 1, 2, 3, and 4, we can switch through templates. So I'm using the geometric mode. And what we might want to do here is basically change the number of cells resolving the thickness of the loop, or the width of the loop. So that's a very classic example here. So now we can basically go down to our thickness parameter. And again here, we might just want to do this in the first step. Let's start with just the Z-axis. So I'm going to open the ganging properties. But essentially this allows us to address certain areas of the geometry without actually resolving the grid in a total region. In addition to that, let's have a look at this template concept in a further step. So basically what has happened here, as I've edited the settings here, the template moves into a new state, so it has now these brackets here, parentheses, and this means it's now in a state which is no longer saved as far as the default settings are concerned. So I'm going to open the template editor here, and what I can do now is basically create a new template from the settings that I have here, and then I can still actually go and edit the template further with the template editor. So I can use some default scaling that I might use regularly. I can change the unit, I can leave it in wavelength. We might want to rename this more meaningfully, and from now on basically I can always apply this template to any simulation or grid settings that I'm working on. So you can apply it to selected objects. The custom templates will now automatically appear in the template menus and are automatically assigned shortcut keys. So from basically 5 to 9, the first 5 custom templates that appear will automatically have those shortcut keys. So that's pretty convenient and a very new concept which will become a lot more useful as we work with more grid settings. So let me just try to illustrate here also the idea of using these different unit types. So one of the new units that we have defined now also is referred to as number of cells. So the first 2 units are quite intuitive, having a wavelength unit and a metric unit. The final unit allows us to actually specify the number of FTTD cells within a certain region. So an example here might be that in the Z direction we would like to only have 3 cells or 5 cells. So I switch the unit for the source to number of cells. I'm going to activate the settings here, and I'm just going to change that for the Z property here. I'm going to set that to 3, for example, and we see now that exactly 3 cells have been defined along the Z-axis, covering the region that is occupied by the edge source. So this is a kind of a totally new kind of functionality that we have in Semcad, but is also greatly supported by the idea of having units that are not specific to the global settings, but rather contained within specific regions in the grid. Okay, so what I've done with the previous model here is I've already run a simulation for the model that I set up in advance. Before we get to that, just to show you, or before we look at the results, I'm just going to show you another feature that we've added, which is something that's been quite heavily requested, and that is sort of a connectivity check, which is performed at a voxel level. So when would you need that? Typical example would be if you are having, for example, a complex structure, metallic structure that might have lumped elements and sources that connect different parts, and it might be difficult to actually visualize at a voxel level if you have actually achieved the correct connectivity because of the detail that is in the model. So what we've done is written a test that will basically verify connectivity between different metallic objects as well as edge sources and lumped elements. And this we find under the simulation menu, and it's called connectivity check. That's going to open a little tool for us. In this case, we only have one simulation, but here you'll just select the simulation that you want to evaluate. I press next, and here we only have 2 different objects here that are one metallic and one source object, which are valid for the test. So we want to check the connectivity between both. And finally, we might be interested in the coordinates where the connectivity points have been tested. Let me just deactivate that. And we basically press next here, and I'm going to close this window. The output is written to the message bar, but you can also find it in the console. So basically here we have the connectivity matrix. Each object appearing in the list is written out along with the nodes where the connectivity has been tested. And here we are testing the edge source against the metallic loop. And basically we can see the vector for the 2 nodes. And finally we have a plausibility check, which basically confirms that in this case the source is connected to the loop. What that means visually, if we go and look at the voxels, so you can always, of course, do that visually. We zoom in here. We do basically have connectivity between the edge source and 2 metallic edges of our loop, as desired. So that's basically what that has done here. So that's something useful, maybe not specific to this example, but definitely very useful for more complex examples where you might have many parts and it's less transparent to see these kind of things. So in a last step then, we can just have a look at the simulation results and also have a look at some of the new post-processing features that we have added in 14.8. Probably the most beneficial feature here is a complete rework of our 2D plots. So we've overcome some of the limitations that we had in the past with respect to units and scaling of units. So, and also just generated a much cleaner interface. So I think this is a big step forward here. You can also see we have some sort of probing where you can sort of measure values on the graph. You may want to have something more accurate. So we have updated the old marker technology that we had. So now basically we can track the curve with this new sort of probing function, and using the middle mouse button we can actually add a marker. Here I don't have a middle mouse button, so I'm just going to use the menu here from right click. This will add a marker here. Let's hypothetically add another one here. So you can see the frequency values and S parameter points for those two markers. We might want to do things like do a differential between two markers, and this is done very easily now. We can select the markers, and the difference in frequency and the difference in the S parameters is printed. So fairly simple things, but also very nice features to have, things that you can use on a regular basis, like for calculating the bandwidth of an antenna or reading out specific values there. So those are the 2D plots. Then in addition to that, as far as field data is concerned, we've added one new viewer type, and in addition to that, completely modified the original vector field views that we had. So I'm going to start off extracting the H field here, and what I've done is I've recorded several different frequencies within the bandwidth of the simulation. So I'm just going to look at, in this case, 320 megahertz, and let's also extract a higher frequency, so we'll look at 840 megahertz here. In both cases, I normalized the field to the same power. In this case, just a reference value of 1 watt, just to be able to compare them. And now what we can do, in the first case, let's just look at the sliced field view at 320 megahertz. We'll have a look at the RMS field here, and I'm going to go just below the loop here. We'll get the maximum here. We can go even slightly lower. And basically what we see is a very sort of typical field behavior for a loop. So this frequency is actually the fundamental resonance for the loop of these dimensions. And this can be seen a whole lot easier than if we now move over to our vector field. So I'll extract the data here. So, and I'm just going to show the vector field here. Let's make this a bit larger. And here you can see some new functionality. So firstly, we use the same color scaling that we have for all of our other sliced views. In addition, now we can actually scale the arrows. So based on the magnitude or amplitude of the field at those locations, the arrows can be scaled. And this gives it a sort of much more intuitive feel